Every 10 minutes, somewhere on Earth, a miner writes a transaction that pays themselves 6.25 brand new Bitcoins, coins that didn't exist a second ago. So why can't they just write 1,000 Bitcoins instead? The answer reveals how Bitcoin's entire issuance model works, and it lives inside two tiny pieces of data, the Coinbase transaction and the 80-byte block header. Meet Jing. She runs a full node and a mining rig. Her node sits in a loop. First, it listens to the peer-to-peer network and collects pending transactions into a waiting room called the mempool. Second, it picks the most profitable transactions and assembles them into a candidate block, a proposed block that isn't valid yet. Third, it races every other miner on Earth to find a proof of work, a hash below the network's difficulty target. Fourth, when someone wins, Jing's node accepts the new block, drains those transactions from the mempool, and the loop restarts. Every block begins this cycle the same way. Now zoom into that candidate block. The very first transaction Jing places is special. It's called the Coinbase transaction, and it's the only transaction in all of Bitcoin that creates new coins. Every other transaction spends existing unspent outputs, UTXOs, moving money that already exists. The Coinbase has no input UTXO. It conjures coins out of thin air by protocol rule and sends them to an address Jing controls. This is how every single Bitcoin in circulation was born, one Coinbase transaction at a time, one block at a time. How much does Jing pay herself? The reward equals the block subsidy plus the sum of all transaction fees. The subsidy started at 50 Bitcoin per block back in 2009, and it halves every 210,000 blocks. At block height 750,000, we've passed 3 halvings. So the subsidy steps down like this: 50, then 25, then 12.5, then 6.25. So the current subsidy is 6.25 Bitcoin. Now add the fees. Every normal transaction's inputs exceed its outputs, and that difference becomes fee income for the miner. If fees total half a Bitcoin, then Jing's Coinbase transaction pays out 6.75 Bitcoin in total. Subsidy plus fees. That's the entire formula. So why can't Jing just write 1,000 Bitcoins? Because every other full node on the network independently runs the same subsidy formula. If Jing's Coinbase claims more than the protocol allows, every node rejects her block on site. Her proof of work is wasted, her electricity is gone, and the next miner takes the reward. Consensus rules, not trust, keep issuance honest. The math is checked by thousands of computers in parallel. Let's open up the Coinbase input itself. A normal transaction input has 4 fields: the previous transaction's ID, 32 bytes, the output index, an unlocking script, and a sequence number. The Coinbase input uses the same slots but fills them with placeholders. The previous txid is 32 0 bytes. There is no prior transaction. The output index is hex FFFFFFFF, a sentinel value meaning none. And where the unlocking script would go, the Coinbase puts anywhere from 2 to 100 bytes of arbitrary data. No signature is needed because there's no UTXO being unlocked. What goes in those arbitrary bytes? In January 2009, Satoshi mined the Genesis block and embedded a newspaper headline. The Times, 3rd January 2009, Chancellor on brink of second bailout for banks. Part timestamp, part political manifesto. Proof the block couldn't have been mined earlier, and a comment on the financial system Bitcoin was built to replace. Today, miners stuff this field with extra nonces, counters used to vary the hash, and pool identification tags. One important rule: BIP34 requires version 2 blocks to begin the Coinbase data with the block height, encoded as a script push. That prevents 2 different blocks from ever sharing the same Coinbase transaction. With all transactions assembled, Jing builds the block header. The 80 bytes she'll actually hash billions of times per second. The header has exactly 6 fields. First, version, 4 bytes, which signals which consensus rules apply. Second, the previous block hash, 32 bytes, which chains this block to its parent. Third, the Merkle root, 32 bytes, a cryptographic fingerprint of every transaction in the block. Fourth, the timestamp, 4 bytes in Unix seconds. Fifth, the target, 4 bytes, the difficulty threshold in compact form, called bits. And sixth, the nonce, 4 bytes, a number Jing increments to vary the hash output. Add it up, 4 plus 32 plus 32 plus 4 plus 4 plus 4 equals 80. That's it. Jing runs SHA 256 twice over these 80 bytes, and if the result is below target, she wins. How do thousands of transactions fit into 32 bytes? Through a Merkle tree. Jing takes the ID of every transaction, pairs them up, hashes each pair, then pairs those hashes, and so on until one root remains. If a row has an odd number, the last entry is duplicated. That single root commits to every transaction at once. Change any 1 byte in any transaction, and the root changes. Since SegWit, there are actually 2 trees, one over txids that fits the header, and one over txid stored inside the Coinbase. The header only needs the txid root. Step back. The Coinbase transaction is where Bitcoin's monetary policy is executed, not by a central bank, but by every node verifying every block according to one shared formula. The 80-byte header is what miners actually hash, and everything else, every transaction, every fee, every Coinbase byte, hangs off those 80 bytes through the Merkle root. Change anything in the block, the root changes, the header changes, the proof of work is destroyed. That's why Satoshi's Genesis message still sits there, 14 years later, untouched and unforgeable. 80 bytes and the Coinbase transaction, the smallest possible data structure that does the largest possible job.